little bit. So up until now, what we've done is the first chapter on mathematical preliminaries of mechanics, the second chapter of kinematics, where we studied how to describe motion using the deformation map and the deformation gradient and so on. And the third chapter was all about internal forces, stresses, and how they relate to tractions. How can we make sure that the bodies or a deformable body is in equilibrium? And then we were going to start fourth chapter about where we were last time. And I assigned this actually as a reading assignment, so I'm sure all of you read it multiple times now that you're all good students. So we can go much faster through this. So actually what I'll do is I'll sort of highlight the need for material properties first, and then we'll go into what different types of material models that you might be used to. So in the context of solving a structural mechanics problem, something like this, we have seen that again and again in the course. We laid out, I think maybe in the very first couple of lectures, the unknowns that we are solving for. There's a displacement field, which means you need to find the displacement vector as a function of x at every point in the deformed configuration, or actually this should be z in the undeformed configuration. But you know that that's just the a slight difference where you express that displacement field either as an Eulerian or a Lagrangian variable. So how many scalar fields does this represent? Displacement at any point in the body. This is clearly a vector field, right? It has three components. So indeed there are three scalar fields behind this. I'm just counting the unknowns right now. Unknown fields, I should say. So these are three scalar unknown fields corresponding to displacement. If we assume that the linearized strain, the linearized strain or the Lagrangian strain is symmetric, then there are 6 independent scalar fields behind that, right? That's what we are trying to find. And then there are 6 stress components. Of course, assuming stress is symmetric, there are 6 stress components that we need to find at each and every point in the body. So a total of 3 plus 6, 9 plus 6, 15 unknown scalar fields that we are looking for at each and every point of the body. And we need 15 scalar equations, field equations, to be able to find them. And let's see how many do we have. We know that in order for this body to be in equilibrium, we must have this equilibrium equation satisfied point-wise, at every point in the body. So that gives me 3 equations right here, right? I have already assumed here that the stress tensor is symmetric. So S is equal to S transpose is already been used. There is this relationship that we saw for linearized strain is equal to half of grad U transpose. That's the strain displacement relationship. That was equilibrium. There's a strain displacement relationship. How many scalar field equations in here? It's relating 6 strain quantities with 6 tensor quantities of the gradient of their displacement. So indeed there are 6 field equations here. And then we have some boundary conditions. So I'll also call these 3 as the governing differential equations, and these 2 as the boundary conditions. And I pointed out last time, I think, that U is equal to UD for every point on deformed portion of A sub D, which is the portion of the boundary that has displacements specified. And the other part of the boundary is the tractions, the boundary where the tractions are specified. And at each point where tractions are specified, we must have the Cauchy stress traction relationship obviously satisfied, but that has to be specified as some external traction acting on the body. For example, in this case, this was pressure on this part of the surface. So the first 3 governing differential equations have to be satisfied at every point inside the body, phi of B. in the deformed body. The other two are boundary conditions that must be satisfied at each point on the boundary of the body. So in all, we have 3 plus 6, 9 scalar field equations, and we have 15 unknown fields. So what obviously we need is 15 minus 9, 6. We need 6 uh, constitutive equations that relate stress and strain fields, and that's exactly what we are going to try to develop here. So in order to develop constitutive material properties, as you can imagine, there are infinitely lots and lots of materials in the world, and each material behaves differently from other materials. But what people did was to try to identify classes of materials that behave similarly, and then they tried to find out certain material properties that would help them uh, uh, kind of model the material behavior so that they can relate stress and strain. Now, the only point that I'm trying to make here is that no matter what material model you have, which relates stress and strain, that is never going to be able to model the material's actual behavior exactly. It's a model. Entire continuum mechanics is a model. There's no such thing as a continuum. Every material at the fine scale is full of atoms and molecules. But we have assumed that that's a continuum, and we are going to try to develop material models that relate stress and strain for a particular type of material. So there are some general principles in developing these types of models that relate stress and strain. So these are some of the principles. I'll try to describe them quickly here. One is deterministic, which means that if you have a material model and you give so what does a material model do? It takes in strain and it gives out stress. You give me strain, I'll tell you what the stress at that point is. And that's another important point, that each of these material models that we're talking about describes the material at a particular point in the body. The body itself may be made of different materials, like reinforced concrete. Part of the body is steel, part of the body is concrete. And even concrete itself is made up of multiple different types of constituents, right? Coarse aggregate, fine aggregate, silica, sand, water, air. So depending upon where you are measuring the material properties, within a deformable body, the material itself differs, and therefore your material model should differ from point to point. All we are talking about is a material model that relates stress at a point to the strain at that point. Okay. So the first thing is that the material model has to be deterministic. If you give me one strain, I should always give you back the corresponding stress for that amount of strain. It should not be that today you give me one strain and then tomorrow you give me the same strain back, and on 2 different days I'm giving you 2 different answers. Okay, so that's what deterministic material model is. There is something called local action. So by and large, most of the constitutive models are local, meaning that in a deformable body, if I go to a point, you give me the strain at that point, then I don't need any other information uh, about uh, strains at other points in the body. Strain at that point is sufficient to decide the stress at that point. Okay, which means that um, so the stress at a point depends only on the state of strain and gradients possibly at that point. There are other different types of non-local models where people actually try to find a measure of stress by looking at a point at the particular point and a small neighborhood of that point. So those types of models are called non-local models, but by and large, most of the constitutive material models that people have follow this local action, meaning stress at a point is a function of the strain at that point. We've already talked a little bit about observer objectivity or material frame indifference, which means basically that but whatever relationship between stress and strain you develop has to be observer independent. Meaning, if there is a physical experiment going on and there are two different teams of observers observing the same experiment, measuring changes in lengths, measuring forces and tractions and all that, then the relationship between material stress and strain that they both these teams develop have to be equivalent, have to be consistent with each other. Uh, Two different observers observing the same experiment cannot come up with two different material models. And finally, laws of thermodynamics must be satisfied. So let me ask you this. How many laws of thermodynamics do we have or do you know of? Two, okay. Well, I guess there is a zero. Well, let's first talk about the first law of thermodynamics. So what's first law of thermodynamics? Conservation of energy. So that in a closed system, you cannot create or destroy energy. That's so any material model that you have, if there's no, if you have a closed system, no way of heat to escape or anything like that, then whatever energy is stored in that closed system can transform from, let's say, potential to kinetic energy or something like that, but you cannot destroy or create energy. Fine enough. That's first law of thermodynamics. What's the second law of thermodynamics? Right. The change in entropy is always greater than zero. What is entropy? It's a measurement of the disorder in a system, and that's a very sort of a general definition of entropy. But essentially, what the second law of thermodynamics says is that there are some irreversible processes in the world that you cannot reverse some deformation. For example, if you have plasticity, you take a steel bar and if you bend it like that and you create like a cripple the material in here, that material goes plastic deformation in that range, and then if you straighten it back up, it won't go back to its original state. Okay, so that's a irreversible process. And another example that I like to give is, for example, that um, if I have this object, if this object is lying on the table, and then if I raise it up to a certain height, then I've added potential energy to this object, right? Now, if I drop it, it goes back to the table, and it made a sound. It probably made some heat, and that sound and heat is lost to the environment. Okay, to, let's say, this closed room. Now, if I somehow manage to capture all that energy of that sound and the heat that was lost and put it back into this object, will this object go back up to this original height? No, that's an irreversible process, right? So, so that's basically what laws of thermodynamics say. And there's, of course, I was telling you about the zeroth law, which says that 0 Kelvin is the minimum temperature that that you can have in a body. So these are some general principles that any material model must satisfy. Um, Predominantly, people have come up with these two different types of materials, and just to be very, very general here, there are elastic materials and there are inelastic. Anything that is not elastic is inelastic. There are lots and lots of different types of inelastic models. And a particular type of elastic model that we will be looking at is called the hyperelastic model. There are hypoelastic or viscoelastic models. Now, I'll talk about those very briefly, but very quickly, I'm going to rely on your understanding of material behavior a little bit. You know, we just talked about what plasticity is, that there are some, after a point, if you deform a material, then it goes into plasticity, an irreversible process. And you have this viscoelastic and viscoplastic type of models. Any idea what those might be? What is viscoelastic or viscoplastic? Yeah, so visco essentially means that there is time dependent behavior in there. A material may be elastic or maybe plastic. If I let's say have this beam, cantilever beam, if I hang a load at the end of the beam, then it will take some time for the beam to deform to go to its final state. And if you're actually taking into account dynamics, then it might have oscillations or something like that. But let's say even if you go to a very small, uh, uh, if you leave that load slowly, then it will take some time to go to its final deformed state. If it is not viscoelastic, if it's just elastic, and if I drop that load on here, then it oscillates and goes to its steady state position, right? uh, which that steady state position is achieved, at least in the static sense, instantaneously. But in viscoelastic models, viscoplastic models, it takes time for them to happen. There are damage models that try to capture how a particular model, like smeared crack models in concrete. I don't know, maybe some of you may have used some of these types of models that try to mimic damage in the materials. We are predominantly going to be looking at the elastic material models. So in elasticity, a very fundamental principle is that when you apply a load to a body, if it's an elastic body, you apply a load, it deforms, you leave the load, it comes back to its original position. That's definition of elasticity. Okay. Um, but there are some consequences of that. One of them is that an elastic material is not history dependent or path of loading dependent. It's path independent, meaning that if I have this elastic body, if I am going to apply a load of say 100 newtons onto this body at the tip, then whether I apply that 100 newtons in 10 newton increments or 100 newton increment or minus 100 and then plus 200, it doesn't matter. The final configuration of that body is going to be path independent. That's what an elastic history independent or a path independent material means. And of course, it also means that the stress in the body is going to be a function only of the current state of strain, not the history of strain of this body that it might have gone under. If I have a certain deformation, knowing that deformation, I should be able to tell you what is the stress at each and every point is. I don't need any past information for that. So these are certain consequences of this. And um, your favorite model probably is the Hooke's law, which actually I don't like the term law. It's a model that relates uniaxial stress to uniaxial strain, and that's a very restricted type of model. So let's actually try to adapt that model into the framework that we are going to be looking at, so that we can extend these types of models to more general 3D stress strain behavior. We know that in one dimension, if you have a bar original length L naught, you apply some force to it, the bar extends by some amount small delta L. Now, Hooke's model would say that force divided by area of cross section is going to be, so force is equal to, first of all, proportional to change in length by some factor. Force divided, if I divide through by area of cross section and L naught on top and bottom here, then I get this relationship that stress is equal to some constant times strain. What is that constant? Young's modulus. So you might be used to denoting Young's modulus as E, but just to be consistent with the book, we are going to be defining Young's modulus as this capital C. So stress is equal to Young's modulus times strain. In the 1D case, there are lots of assumptions behind this relationship. First, that the bar is uniform. Everywhere in the bar, the same cross section, same material, the stress has to be uniform. So this measure of strain is uniform everywhere. if the bar is changing in cross section, then that relationship would have to be applied pointwise. Okay, then that relationship would have to be applied pointwise. Now this is a linear elastic relationship, in which essentially says that the stress and the strain are related linearly. You load it, you build up stress, unload it, come back to zero. Now it's not necessary for elastic materials to be linear. You can have non-linear but elastic material models as well. And an example of that would be this curve that I have this material, I'm going to stretch it, and at every point as I'm stretching it, during the stretching process, the stress builds up faster in this region, slower in this region, and faster again in this region. But when I unload, it comes back exactly on that path. Okay, so this is an example of a non-linear elastic material model. And a characteristic of these elastic material models is that the work done at a material point of this body, at each and every material point of this body, is equal to the energy stored in that. So if I extend this bar, then you can imagine that at each and every point, stress and strain build up. Now, so when I stretch this bar, like stretching any spring, what happens if I have a spring that is relaxed, and then if I stretch it by some amount delta, am I storing energy in the spring? That's potential energy I've stored in the spring, right? When I leave it, it comes back either with kinetic energy, or if I leave it slowly, then it has the ability to do work against for that stored energy, right? So if you do work on a material point, you get energy stored. If you have energy stored at a material point, then you have the ability to do work with that material. So I'm going to cast this work done in a form that will allow us to define some measure of energy stored in the material point. So for that, we are going to take a look at this total work done as we are extending this bar, as we are applying this force. So if you think of this force, I'm going to move that force here, and then initially that force is 0, but then I slowly start to increase that force to reach its final value, where the bar looks like that. So the process is, I have this bar, I slowly apply that force and reach a final value F, and I'm going to try to measure the work done in that circumstance. So force will be a function of the change in length, delta L, and maybe what I should also do is take an aside here. So if I have this bar, I'm applying some force to it, F, as a function of, which will be a function of displacement. So if you were to plot, let's say, delta L and the force F, then you could, we are talking about, let's say, a linear process here. Then as delta L changes, the amount of force needed to achieve that delta L also changes linearly. It could be non-linear, but let's for now, let's say it's linear. So the area under the curve, let's say going from here to a final value of this delta L naught that we had in this case, the area under the curve would be the total work done by that force, correct? And that area under the curve is nothing but this integral of f dl integrated between 0 and delta L. That's the total work done. At a particular point. So we are actually, this is total work done over the entire length of the bar. So this is, and then what I'm going to do is to just express it in terms of stress and strain. So we're going to make some substitutions. Integral f divided by a, that will give me stress. Since I've divided by a, I need to multiply by a, and This dl divided by L0, that was the original length. That's essentially the strain at a particular level of deformation at an instant. So I'll multiply those two A and L0 out here. A times L0, the cross-section area times the length, is the initial volume. So that is the volume of the body, and this, so let me see. So this is the volume of the body, this is the strain at a particular level of deformation, this is the stress at the same corresponding level of deformation. So if I were to rewrite this, we would get integral over the volume of the body times stress at a particular level and times strain and dV. Actually, so, and this here is actually d epsilon. So d epsilon integral between 0 to epsilon and dV. What we have inside this volume within the square blue square brackets, we have a term that captures the energy stored at a particular point in the body. If you integrate that energy stored over the entire volume of the body, then you have the total energy stored. Yeah, Vigita. So I have, you're correct that if A is A times L, 0 is the volume of the body. Now in this, I've assumed that the cross section is uniform. But if the cross section is not uniform, then what you are doing is you are taking this quantity. So maybe I should write that intermediate step. I'll move this out. Integral dV is V, correct? And if I do this, does it make sense? Is this quantity equal to this blue square bracket term? And then V is equal to integral dV. And that's assuming that this quantity is constant everywhere over the volume of the body. If this quantity is not constant, then I would have to move it inside the integral and keep for a body that has non-uniform cross section or non-uniform material properties. Material could be different or cross section could be different of this body from point to point. So essentially what we are saying is that we are going to measure the energy stored at each and every point in the body, and we are going to integrate that over the entire volume of the body. So this quantity within this blue square bracket is called the strain energy density function, and it's denoted by phi of epsilon. Okay. And any material that we can express in this form, whose behavior we can express in this form, that has a strain energy density function associated with it, is called a hyperelastic material model. So your the material model that you've been predominantly using till now, the Hooke's material model, is a type of a hyperelastic material model. Okay. The whole idea is that in these types of models, if we do work on the material, it stores energy, and we can express that energy as a density function, meaning each and every point has some energy stored, and we are going to be able to try to write what that stored energy density function would look like. All right, so excuse me. For the one-dimensional model, let's take a look at what this means. We have we said that the stored energy density, this will be stored at each and every material point. So from point to point it will be different. This is the expression that we came up with, that the stress as a function of strain integrated through the deformation process from starting from some initial zero strain to some final strain gives me the strain energy density stored. A direct consequence of that, if you take the derivative with respect to epsilon, is that d phi d epsilon, that if you're given the strain energy density function, then take the derivative of that function with respect to epsilon. That would be the instantaneous strain, instantaneous stress at that level of strain. And if the stress strain relationship is linear, like the Hooke's model, then you can show that strain energy density is half times the Young's modulus epsilon square. Very easy to verify. If you take one derivative of that, we get stress is equal to C times epsilon, right? First derivative with respect to epsilon gives me C times epsilon. C is simply equal to d epsilon, d derivative of stress with respect to epsilon, and equivalently it is the second derivative of the energy with respect to epsilon. So at any point, if I have a hyperelastic material, at a particular point in the body, I'm trying to relate stress and strain using this strain energy density function. If I know the function, I can take the derivative of that function to get stress at that point, another derivative to get the rate of change of stress as strain changes. So that's a one-dimensional analogy with something that you know, the Hooke's material model. Let's now try to generalize this to 3D. And of course, in 3D, we have stress tensors, strain tensors. For now, we'll work with the linearized strain tensor, not the full green Lagrange strain, but the linearized strain. And in the same way that we did strain energy for a one-dimensional bar, I'm going to write the strain energy stored at each and every point of a three-dimensional deformed body. Okay, so what we are doing here is writing this as stress at a particular point. Go to any point in this, stress double dot, I'll talk about what that means, is double dot d epsilon, which is exactly the same as what we had here, stress times d epsilon. Okay, so stress double dot with d epsilon, I'll maybe define what that means. That's the contraction operator. And what that means is that S double dot d epsilon as a tensor is equal to Sij d epsilon ij. And again, I'll take an aside here. So we are saying Sij d epsilon ij. What does that mean? If we follow the initial notation, S can be represented as a 3x3 matrix, d epsilon can be represented as another 3x3 matrix. What term does this, or what does this mean in terms of these two operations? I is repeated, j is repeated. So total number of terms, 9 terms, and they are all going to be summed up, right? Since I and j are repeated, it means that there is a sum over I going to 1 to 3 and j going from 1 to 3. So what you would do is to take the stress tensor and the incremental strain tensor, multiply each of these corresponding components, and the result would be a scalar, vector, or tensor. Scalar, because indeed this is a sum over all the terms. We are not just taking this term multiplied by this term and putting it in a matrix. It would be a scalar. So maybe I'll just write it as a scalar here. And that scalar, when you put in here, integrated over the entire deformation process, should give you back a scalar, which it does. So that would be the strain energy density function at a particular point. And We can also express this in a slightly different way. So that would, if we think of the deformation process as a function of time, I can write that stress double dot with rate of change of strain. That's what the dot means. So it's d epsilon dt, and I'll have dt out here, integral over the deformation process from 0 to t. And this quantity here is called stress power. And it's like the rate of change of internal work, rate of internal work done. So that gives me the strain energy density stored at a particular point. If you integrate that over the entire volume, that would give me the strain energy stored in that entire body. So this integral that I have written out here is the same as this corresponding integral that I have here in the blue brackets.
I think this kind of expression for strain energy is suitable for small deformation situation.
No, not necessarily. This is not only for small deformation. The reason for using this small deformation or the linearized strain tensor is because we are using Cauchy stress here. Cauchy stress is work conjugate, if you sort of understand that term, is work conjugate to a linearized strain. If you go to second Pila-Kirchhoff sigma tensor, that is work conjugate to your Green-Lagrange strain. So exactly same relationship, it would still hold for large deformation cases also. But okay. So what that tells me is, if I take the derivative of this function with respect to time, this is phi dot d phi dt. That would basically just take out this integral, and what I would have left would be the stress power. Essentially, it is saying that at a material point, if I do external work, the rate at which I'm doing external work is going to be the same as the rate at which I'm storing internal energy in that point. So all we've done is just added a rate term to that. It's pretty much exactly the same as saying that work done at a point is equal to the strain energy stored at that point. Not only that, but the rate at which we are doing work is also being stored at the same rate of energy stored. So in the same analogy with the 1D case, stress tensor would be the derivative of the phi scalar function with respect to, let me see if I want to use phi dot. This stress tensor, if I take derivative with respect to the strain tensor, gives me the stress tensor. And in terms of components, what that simply means is that each and every component of that stress tensor can be obtained by partial phi, partial epsilon ij. Okay. I'll come to give you some examples of these strain energy density functions, and we'll see how to actually calculate stress if you're given a strain energy density function by taking derivatives with respect to epsilon. We'll do that maybe in a couple of slides. We also want to, I also want to point out a little bit of consequences of this. Just like in the linear, just like in the one-dimensional case, when we say that stress is a derivative of the strain energy density function, and if the material model is linear, for the linear case, we were able to relate stress with strain with some constant, right? In three-dimensional cases, this is a tensor, this is a tensor. So what we need here is a fourth order tensor. Now till now you've been dealing with second order tensors, where there were two subscripts, right? If T is a tensor, Tij, it had 9 components. These are second order tensors. What we have now is a fourth order tensor, meaning that there are four indices in there. Since we are relating a second order tensor to a second order tensor, you remember when we said a second order tensor is something that acts on a vector to give me another vector? That's basically a second order tensor. And in general, a general nth order tensor acts on a m order tensor to give me an n minus m order tensor. So a tensor is something that acts on a tensor to give you back another tensor. How about that for a definition, right? um, so the whole thing here is just that a fourth order tensor would act on this strain second order tensor to give you a second order stress tensor. So in effect, as I said, there are four indices, which means how many total number of elastic constants are we talking about to relate stress to strain? There are 9 strain components, 9 stress components, and each one of those, pick any one of those stress components, you have 9 different strain components to relate to it. So there are 9 times 9, 81 material constants to define. I'll come to you, Vikita, just a second. So 81 material constants that we are talking about. Go ahead, Vikita. Question?
So when we say mth order tensor acts on nth order tensor to give n minus nth order tensor.
That's right.
And when we say that a second order tensor acts on a vector to give a vector, that indirectly means that a vector is a single order tensor.
Right, right. So a vector can be viewed as a order 1 tensor. Yes. Now there's some discussion about this. There are two types of bases people use: contravariant and covariant bases, and there's some complication to that. But yes, in the context that we are using, vector can be thought of as a first order, as a 1 order tensor. But okay, let's get back to this. We are talking about 81 elastic constants, and if you look at the next page of the handout that I've given you, we have this big, huge matrix that I've written the stress tensor as a vector, right? As a 9 cross 1 vector. And on the right hand side, I have a 9 cross 1 vector of strain components. And indeed, it is this 9 cross 9 matrix, 81 constants that we are talking about. I'll point out that this is a little bit of abuse of notation because stress is not a vector, right? Stress cannot be written in this form. Strain cannot be written, should not be written in this form. So indeed, this is abuse of notation. But if you were to think of the left-hand side as a 3 cross 3 matrix, think of this strain as a 3 cross 3 matrix. What do you think would be in between? What does how do I visualize a fourth order tensor? It would be, in terms of matrices, it would be a four-dimensional cube. I can 3-dimensional cube I can visualize. Fourth dimensional cube I cannot visualize. But and maybe in a physical context, what that means is, you remember when we talked about second order tensors, we said it takes an arbitrary sphere of vectors to an ellipsoid of vectors. That's what a second order tensor that was what we visualized. Now imagine on the left hand side all possible ellipsoids, right? On the left hand side there's all possible ellipsoids of different shapes, and on the right hand side another set of all possible ellipsoids. The relationship between those two sets, all possible ellipsoids of stress at one point and strain at one point, a relationship between those all possible ellipsoids is what a fourth order tensor would look like. But anyway, the bigger problem with this is that if I have to define a material, if I define a material with 81 elastic constants, then I would have to do 81 different types of experiments to try to determine each one of them, which is simply unmanageable. But there's some good things about it. We know that stress and strain are symmetric. So Cij and Kl, this KL and this KL are the same. So the second two indices correspond to the indices of the strain. The first two indices correspond to the indices of the stress. I know both stress and strain are symmetric. So it shouldn't matter if I interchange Ij or interchange K and L. So Cij KL should be equal to Cij Lk, interchanging KL for strain, or it should be equivalent to Cji and KL, interchanging the indices for stress, which means that if essentially that I am reducing now from 9 components of stress, 9 components of strain, down to 6 and 6 components of stress and strain, correct? Immediately that means that I've reduced my number of elastic constants down to 36, right? Which is that blue box on that figure that I'm showing you. These are the unique components of stress. The other 3 are just repetitions of the off diagonals. Similarly for the other 3 components of strain. So all I need is this 36 constants. Everything else is a repetition of what's already in there. So that definitely helps us a lot in reducing the material properties. Further, there is a major symmetry of this Cijkl, and what that means is actually that I'll take a side here again, that we can show that for Hooke's model in 3D, the strain energy density function is given by half times epsilon ij Cijkl epsilon kl. Very similar to what we had for the 1D case, half times C epsilon square, or half times epsilon C epsilon, which is what we have here, half times epsilon C epsilon in 3D. Now, it doesn't matter whether I use epsilon ij here or here. The order of that does not matter. So that's what the major symmetry of Cijkl means, which means that I have to worry only about the diagonal components, that this itself is symmetric, right? So only about the lower triangular or the upper triangular constants we have to worry about. The off diagonals are symmetric. So how many constants do we have now? Only lower triangular. 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 6 times n plus 1 times n. So 6 times 7 divided by 2, right? So that's 21 constants. You can count them, the lower triangular constants. That would be 21 constants. So that's another reduction of some number of constants, but still we have way too many constants to be determining. I'll very quickly go to this aside, and then since I've already talked about this, this aside about how to work with this fourth order tensors, and then we'll be done for today. Let's say I have a 4th order tensor T, a 2nd order tensor S. T acting on S is defined in this way. So we have this as a 4th order tensor can be thought of as a dyadic product of a two or 2nd order tensors. What we'll do is take a dot product of V with B and a dot product of U with A. If you remember, we did something similar for 2nd order tensors when we were doing with the dyadic product. So what that gives me is U dot A, that's a scalar, times another scalar, which is V dot B, and then the remaining thing is in the direction of this 2nd order tensor, S dyad T. Okay, so that's how 4th order tensors work on each other. So to explicitly say that, for the tensor basis, EL dot with EM, EK dot with EM, what do these two things give me? Delta Km, right? EK dot with EM is delta Km, and EL dot with En is delta Ln. in the direction of EI dyad EJ. EI dyad EJ. So if I apply that to this relationship that we had written out for stress and strain, I have Cij fourth order tensor basis times second order tensor basis. What I get is EL dot with En, that was delta Ln, K dot with M, that's delta Km, and I'll contract that K out with this K, let's see, sorry, this, I'll contract out this M with this M and replace it with K. I'll contract out this N with this N and replace it with L, and that gives me Sijkl is Cijkl times epsilon KL. So this is just a verification that the stress and strain relationship that we had on the previous page is indeed given by a linear relationship, but with lots of constants, 21 constants for now. And okay, so let me stop here and then I'll continue on Friday.
I think I stress.